Basics of DC, direct current, detailed description. The image explains the basics of direct current, DC, which is one of the two main types of electric current used in electrical and electronic systems. Direct current, DC, is the flow of electric charge in only one direction, from the positive terminal of a power source to the negative terminal through an external circuit. Unlike alternating current, AC, the direction of DC does not change with time. Most electronic devices, such as mobile phones, laptops, computers, LED lights, calculators, toys, cameras, and battery-powered equipment, operate using DC power. Common DC sources include batteries, solar panels, DC power supplies, and fuel cells. Since the voltage remains nearly constant, DC provides a stable and reliable source of electrical energy for electronic circuits. The left side of the image shows the DC waveform, where the vertical axis represents voltage, V, and the horizontal axis represents time, T. The graph displays a straight horizontal line labeled VDC, constant voltage, indicating that the voltage remains constant over time. Unlike an AC waveform, which rises and falls continuously, a DC waveform does not change its polarity or direction. The illustration also shows a simple battery connected to a load, demonstrating that current flows steadily from the battery through the load and returns to the battery, completing the electrical circuit. Because the voltage remains constant, the connected device receives a continuous and stable supply of electrical energy. The center section of the image presents the essential formulas used in DC circuits. The first formula is Ohm's law, I is equal to VR, which calculates the current flowing through a resistor. Here, I is the current measured in amperes, A, V is the voltage measured in volts, V, and R is the resistance measured in ohms, omega. This formula shows that increasing the voltage increases the current, while increasing the resistance decreases the current. The second formula is the power formula, P is equal to V times I, where P is the electrical power measured in watts, W. This formula calculates how much electrical energy is consumed by a device. The third formula, V is equal to I times R, is another form of Ohm's law used to calculate the voltage across a resistor. These formulas are the foundation of DC circuit analysis and are widely used in electrical and electronics engineering. The image also includes the formula F is equal to 1/T, which defines the relationship between frequency and time period. Although frequency is an important concept for alternating current, a pure DC supply has no repeating waveform, so its frequency is 0 Hz. Since the voltage remains constant and does not alternate, the concept of cycles does not apply to DC in the same way it does to AC. The right side of the image presents a real-life example of a battery-powered solar energy system. In this example, a solar panel converts sunlight into DC electricity. The generated DC power is sent to a charge controller, which safely charges a lithium-ion battery. The battery stores the DC energy until it is needed. When a device such as a portable projector is connected, the stored DC electricity flows directly from the battery to the projector, allowing it to operate. This example demonstrates how DC power is generated, stored, and used without changing direction, making it ideal for portable electronic devices and renewable energy systems. The image also provides a practical calculation using Ohm's law and the power formula. Suppose a battery supplies 12 volts DC, and the connected device has a resistance of 4 ohms. Using Ohm's law, the current is calculated as I is equal to VR is equal to 12V divided by 4 ohms is equal to 3A. This means the device draws 3 amperes of current from the battery. Next, The electrical power consumed by the device is calculated using P is equal to V times I is equal to 12 V times 3A is equal to 36 watts. This means the device uses 36 watts of electrical power while operating. These calculations help engineers choose the correct battery size, wire thickness, and circuit protection for safe and efficient operation. A common everyday example of DC current is a mobile phone. The battery inside the phone stores DC electrical energy. When the phone is switched on, the battery supplies a constant voltage to the electronic circuits, display, processor, memory, speakers, and camera. The current always flows in one direction, allowing the phone to function correctly. Similarly, a flashlight uses DC power from one or more batteries. When the switch is turned on, the battery supplies current to the LED bulb, producing light. The brightness remains stable because the battery provides nearly constant DC voltage. Another practical example is a car battery. Most vehicles use a 12-volt DC battery to start the engine and power electrical components such as headlights, dashboard displays, the radio, power windows, and the horn. Even though the engine's alternator generates AC internally, it is converted into DC before charging the battery and supplying the vehicle's electrical system. This ensures that all electronic components receive a stable DC supply. A simple way to understand DC current is by comparing it to water flowing through a straight pipe. Imagine a water pump pushing water continuously in one direction through the pipe. The water never reverses its direction, it keeps flowing steadily toward the destination. Similarly, in a DC circuit, electrons move continuously in one direction from the power source through the electrical load and back to the source. This steady flow makes DC ideal for electronic circuits that require a constant and reliable voltage. In summary, the image explains that direct current, DC, is an electric current that flows in only one direction and provides a constant voltage over time. The DC waveform is represented by a straight horizontal line because its voltage does not change. Important formulas such as Ohm's law, I is equal to VR and V is equal to I times R, and the power formula, P is equal to V times I, are used to calculate current, voltage, resistance, and power in DC circuits. Practical examples, including batteries, solar panels, mobile phones, flashlights, and electric vehicles, demonstrate how DC power is generated, stored, and used in everyday life. Understanding the basics of DC current is essential for learning electronics, electrical engineering, renewable energy systems, battery technology, and the operation of modern electronic devices.